So let's just illustrate this with a simple linear example. Let's take 2 or 3 neurons, right? We're going to have 2 input neurons. And we're going to do a really simple calculation. Let's say we want to calculate the function y equals ab plus c, right? Or y equals ax plus b. Our variable is x. Our constant term is this bias, this bias is actually 1, right? And then what we're going to do is we're going to calculate a as the weight W2 and b as the weight W1, right? So the output here will be y hat equals W2 times x plus W1. And what we want to do is we want to optimize this. So we're going to train this to actually calculate x and the bias to be our best approximation to this system. And the key is, or a key is, we're going to do this with noisy data. It's really easy if you throw in exact values for x and y, right? Then it becomes just, you grab a couple of points and you draw a line through them. But we're going to do this in the presence of noisy data, and our goal is going to be to minimize, well, the L2 distance. We want to take this as close to the correct solution as possible. All right. So we're going to have to install some stuff. If you're running on OS X and you're running it natively, you're probably going to need a few packages. Basically, this will allow you to pop up matplotlib plots. If you can't do this, instead of doing a plot show, do a plot save, and it will allow you to save it out to a file and then view it in any file that can, in any viewer that can view a PNG. But this should, as of in Tensor 1.0, this allowed me to get this running on a Mac. Your mileage may vary. You know, maybe we've given you a number of different ways to get TensorFlow installed. I'd recommend you kind of get this working on whatever platform you plan to use for the lab before you come to lab on Thursday. Or you can run a Docker and update it, right? This is the run command we had before. We did an apt-get update, and then we installed Python TK, Xterm, X11 apps, Qt5 default. And then just to make sure our display is working, Xeyes will pop that up as well. Or you can use your own Python installation, and you can do a pip install TensorFlow, Matplotlib, and PyQt, right? The same thing we installed here. So I did this one, and I actually have this running. And by the way, I did install X11 apps and a bunch of other things. So if I bring this up and we go back to my let's see, let me pop this up here for right now. So just to kind of take this to a good place, or take this to a consistent place. This is my window. I can go to this. We'll look at everything in my window. I've got everything displayed, so I can do an Xeyes, and somewhere this should have popped up some eyes. There we go. Xeyes is just this cute little, come on, move for me. I can see it. There we go. Okay, so didn't quite do what I wanted to do, in that it stretched the eyes instead of actually moving the eyes. But there are some Xeyes being stretched. It's just a cute little program that allows you to see some eyes and actually shows you whether your X installation is actually working correctly. Mine kind of is, despite the fact that I can't get that to pull up the way I want it to. Okay, so I've got that installed. I've already done my pip install. So I've kind of followed through these instructions. So now let's kind of look at what we want to set up. I think we will keep, for now, keep sharing everything. And let me see. Okay. No, that's too. Yeah, that should work. Okay, so let's start. This is my VI editor. Let's see if I can get these things into there. All right. So the first step is just importing. Sorry about that. I hit my microphone. First step is just importing some things. Right. We'll import TensorFlow. TensorFlow Keras is the serial eager execution kind of interface, and we're going to import matplotlib, which is how we're going to plot things. We're going to define some utilities. The first thing we want to do is this make noisy data. So what does this actually do? Well, so make noisy data is, make sure I'm showing the right thing. Yeah. Make noisy data, right? What we're going to do is we're going to take in the equation for our line, right? mx plus b. So this is our overall line shape we want to generate. We want to generate at 100 points. So what we're going to do is we're going to generate 100 samples, 100 noisy samples based around the line y equals 0.1x plus 0.03. So our shape is going to be, we're going to be using vectors. So our shape is going to be 100 by 1, right? So we're going to generate a vector of 100 by 1. And what we'll do is we'll generate a vector x that represents some random numbers between some random numbers between 0 and 1. So we're just gonna generate random values for x. These will be the values along the x-axis, the x-coordinates of the curve we want to generate. And then we're going to generate some noise, and we'll generate the noise to be the same shape as the x, right? It'll be 100 by 1 vector. And this time we want to generate the noise instead of generating it uniformly among the values 0 to 1. We want to generate it with in a normal, right? We want the normal curve, and we're going to generate it with a standard deviation of 0.01. So it's going to be not a lot of noise on it, but it's going to move us away from the line 0.1x plus 0.3. And then all we're going to do is we're going to generate the actual y, right? And we're going to add to that, right? Y equals mx plus b. This is the equation of the line. And then we're just going to add some noise, and we're going to return the two vectors x and y. So this is just going to be our input data. You can assume that the noise came from a sampling process. So we had values at x we wanted to measure, and when we measured them, we had a little bit of noise in the system, and we came out with measurements that were a little off. I don't like how this function was written. Had I noticed this earlier, I would have fixed this. But predict takes a value x and two global constants, m and b, which I don't like. That should have been passed in, and returns what we think the value of y should be. So the idea here is that we're going to walk along, and at each iteration of our model, we're going to take our current estimates for m and b, and we're going to generate a new predicted value of y, and then we're going to compare that predicted value of y. We're going to calculate an error vector that tells us how far off we are from our estimate, and use that to kind of hone in on the correct values by following a gradient descent. And finally, we'll do this squared error. This is going to tell us how far we are away. Given a y predicted and the actual y, it's going to tell us, it's going to tell us how far away our current estimate is from where our current estimate should be. So what we'll do is we'll go through and we will take our noise pairs up x and y's. So this is the true y, right? This is the vector of true y values. This is the vector we get from running x and y through our predictors based on our current estimate for m and b. And all we're going to do is we're going to calculate the squared error. So we're going to add up the distance of each one of these predicted values of y from our actual values of y, take that squared error and accumulate it. And then in our, that's going to be our error function. That we're going to try to do is we're going to try to minimize that as much as possible. And if you kind of study this, that's just essentially we're going to do the least squares error when we're through this. Okay, so now we're going to get started. The first thing we're going to do is we're going to, so we've kind of set up our code. The first thing we want to do is we want to come in here and we want to generate some data. We'll generate our series of x values, right? Those are going to be the random values uniformly distributed between 0 and 1. We're going to do our y values, which are going to be perturbations from, the exact line y equals 0.1x plus 0.3. And just because we're feeling cool, we're going to go through and we're going to plot that and show it. And then we're going to start off by assuming that our current guesses for m and b are 0. Okay, so let's just take a quick second to actually run that. Hopefully this will run. Okay, I have to run it using Python 3. And let's see. There we go. And if we look at it, this is what our data actually looks like. Okay, we have our x values uniformly taken between 0 and 1. Our line should be right in through here, pretty much. And then we just have our little perturbations in the y direction that keep us from being exactly on that line. All right, so we'll kill that. Let's go back to our editing. We set up our variables m and b to be 0 and 1, 0 and 0. And now let's set up to do some predictions. Here we go. Okay. So the first thing we want to do is we want to calculate for each one of our, we want to calculate for our right? This is the actual value of y that we generated from our measurements. We want to predict what that y vector is going to look like given our current model of m and b. And we're going to calculate that as a loss. I'm going to accumulate this loss into a vector because I think we're going to want to look at that. And then we'll just print out how far we are away when we first start. I'm not going to run that quite yet. Let's go to another page. We're going to set up a few things. Gradient descent. The gradient tells us which direction to go, and it tells us the strength of the gradient, but it doesn't tell us how fast we want to step. So if we step all the way, right, if we so we have this learning rate. The learning rate is given a certain strength of the gradient, how far down that path do you want to walk at any one time? So we're going to take a very conservative 5% learning rate. And we're also going to, number of steps is how many iterations you want to run. There are a couple of ways to run this. You can run it for a fixed number of iterations, or you can run it till the error is below a certain value, or you can run it until the error stops decreasing. There are 100 different ways to determine this. We're just going to go for a fixed number of iterations. So we're setting up our number of steps to be 200. We're going to set our learning rate to be to about 5%. If the learning rate's too high, what you end up doing is you end up shooting way past the actual point where the solution is, and you can end up jumping back and forth over your solution without ever getting close enough, without ever approaching it. If the learning rate's too slow, you come down and you're just moving so slowly along the curve that it takes forever to actually reach the minimum value, the solution. So learning rate is something you have to tweak. 0.05 is a good starting value if you don't know anything else. But you may have to play with that for different problems. All right, so let's run what we have here just for a second. So we should be able to run this same way we ran the last one. We're not going to get much else out. I'm not even going to show you the plot because the plot is going to be identical with what the plot was before. But once I close the plot, what you're going to see is that we've now calculated a starting loss, and our starting loss, our starting square, sum of the squares distance is 0.12. We're now going to go into a while loop. So this loop is the major loop of the program. We're going to do 200 steps. Every time through, we are going to calculate our gradient for our answer, right? That's what this TF gradient tape does. And we're going to do it based on predicting x and then calculating the squared error. Okay. This gradient tape, my understanding of it, I should go back and look at it a little bit more, is that it does small perturbations in your calculations within this width loop to come up with an estimate of the gradient. So I believe it's essentially a difference engine, but that would be worth researching a little bit more. Regardless, this is how we get the actual gradient out of it. I'm then going to append that loss to our vector. Again, this is just so that we can at the end plot our gradient or plot our loss function so we can see how the loss changes over time. And then we pull out from the gradient, you know, which way loss is actually increasing with respect to M and B. We are going to subtract from our current M the negative. We're going to subtract from the current M the gradient times the learning rate, and it's, the M gradient, the partial with respect to M, times the learning rate, and from B, the partial with respect to B from the learning rate, right? So this gradient is going to return as many members as we have in this list. It's going to return it based on the loss function. This is where we're subtracting off the gradient times the learning rate to make sure that we're progressing a certain amount in the correct direction. And then every 20 steps, we're going to just print out what our current loss is. And that's just so that we can believe that things are actually working. And by the way, we're doing a lot of stuff here that we wouldn't necessarily, that some of this will be taken care of by TensorFlow as we kind of get more into this whole situation. And why did that not do what I wanted it to? Probably because I didn't copy this. I just highlighted it. There we go. All right, let's see. And so that this will go through 200 times. 200 times we'll calculate the gradient. Of loss with respect to M and B, right? So we're figuring out what direction M and B have to go in order to minimize the loss, subtracting them off from our current estimates of M and B, and then, you know, starting again, calculate the current loss based on the new estimates, and so on. And then at the end, after our while loop, we're just going to do some reporting. We want to know how close we came. We want to know how close we came, right? What's our current estimates for the line? Plot our loss vector, right? We want to see how our loss decreased over time. And then we want to plot both the original data and the line that predicts the original data, and show that. So that'll be 2 additional plots. So this should be all we have to do for this. It's a fairly compact algorithm. What is it? 54 lines. I left some white space in there. Not really all that complicated of an algorithm. Let's run it. All right, so we're set up, we're running. Here's our original plot. That's our original data. We'll now go on. This is how our loss vector goes down. So we started out with 0.12, and after 200 steps, well, after 180 steps, we were down at 0.0001. So we've reduced that by 3 orders of magnitude. Our actual loss plot looks something like this. So you can see that really most of the work we did was in the first 25 or so steps, right? If we look at our setup between step 0 and step 40, we got all the way down to 0.00018, and then in the next 140 steps, we just managed to take out, you know, that, essentially. Okay. Right, so when you look at these plots, you can kind of see most of the work you've done occurs, 40 is out here. After that, there really isn't much being done by this optimization. But getting here took out most of the actual error. That doesn't mean this doesn't get better. And if we kept running it, we might get better yet. But we have removed most of the error. The line we came up with, this should have been 0.01x plus 0.03. And you can see that our estimate for M is off by 0.06 thousandths. And our estimate for B is off by about less than 2 thousandths. Let's get rid of our plot, and now we can look at the actual data plotted. And so this is our the blue dots are original data, and then this teal line is our linear estimate for the data. So this is essentially, this is the same process that we're going to do for our machine learning operations that you'll do in lab. The difference is that in the machine learning operations, instead of having M and B, we're going to have, a large number of variables representing the function, the bias, and the weight input to each of our neurons. Okay, so it's going to be this is a simple version using one neuron essentially. In our examples in class or in our examples in lab, we'll be doing this for hundreds of variables. Yeah. Okay. Yeah, there we go. That brings us pretty much to the end of today's lecture. I do want to leave you with a couple of things. I walked through a very simple one-line. Yeah, go ahead, Kevin. Why don't you let me pull you in. Go ahead. Yeah, Hunter, that was white and gold or blue and gray dress. You there, Kevin? Did I? Yeah, once you're up on stage, you should be able to. I'm not seeing any button that I can do to unmute you. All right. You say something when you're there. Until then, I'm going to keep going through a little bit here. But as soon as you can come in, please go ahead. I gave you a very quick one. This is covered. And by the way, this had to change extensively from the version 1 version. So I apologize for stumbling a little bit there. The version 1 version, we had to actually generate the execution graph, and then we executed the execution graph multiple times while checking the flow. Google does a very good job of walking you through this. What I did was I found this one tutorial online. This was at I think at Google I/O. Was it Google I/O? Or TensorFlow World.
Also, for privacy reasons, that would not be cool. But because this is running client-side in JavaScript, we can do that. And so immediately, you can see all the things that we can do on top of this. There's other models.
This, by the way, is the end of the talk. I was watching it myself. But you should start from the beginning. Right? TensorFlow, Introduction to TensorFlow Beginners. I recommend.
My name is Ashley. I will be your host for today.
Highly watching this before your lab. It covers what we covered here and a little more. So I think you'll find it very useful. There are also, on Google's website, there are a lot of tutorials from their workshops. You'll have to kind of play with these a little bit, but they're good. If you want to get more exposure to TensorFlow and you want to try it out on some harder problems. These are a very good place to go to get some examples. And there are other links here as well. We're going to do a version of a neural net to recognize articles of clothing. There's another one that recognizes cats versus dogs. You can see that here. And then there's all sorts of other Colab research. Colab is an online resource for looking at looking at TensorFlow and other projects. Tensorflow.org and ai.google.com education. All of these are good links to kind of learn more. I'm just going to kind of leave you with that for now. Kevin, are you there yet? No. Do you want to just pop out and pop back in again, or did you already try that? The unmute button is broken. Hunter, Jeremy, could one of you try popping in? Can you say something?
I think I'm good. I don't know what's going on.
Yeah.
Maybe a different browser?
Huh. I don't particularly have you muted though. I mean, I haven't. I'm not the one that's muting you, Kevin. Just so you know. No, because we had people coming up and asking, so the post is that it may require administrator privileges, and I'm thinking maybe that is true, but we did have people coming up on stage before, right?
We definitely did.
Yeah. Oh, in fact, we had people presenting. This could be a real bummer if we can't get this working. Does somebody else, while we're waiting for Kevin, does somebody else want to come in and at least let us verify that this is a problem with his screen as opposed to our screen? Because that would be useful to know before the next iteration. So I think I have Kevin is in the room now. Does somebody else want to raise their hand? I'll bring you in as well. Nick? Okay, let's see if Nick can come in. I've got Nick and Prasant.
Can you hear me?
We can hear you just fine. And I invited Prasant as well. Okay, so
All right, do you want to check screen share?
Sure.
Yeah, it looks like it's good on my end.
Okay. So Kevin, I don't know what's going on, but it seems like it's with your system. Do you want to try typing the question in, or do you want to yeah, I think that may be right. Maybe your browser's lack of permissions. Do you want to try typing it in, or do you want to try to get this fixed and ask on Friday? I'm happy to go however this makes sense. So basically the question was, how do you correct the noise of the line if you have knowledge about what the line is supposed to be? So so what we were trying to do was kind of the opposite of that, right? We were trying to calculate the line given a bunch of noisy data. I mean, if you know what the line's supposed to be, the error function is still the L2 the L2 error function is still the sum of the squares of the data from the line. So you could still use that as your loss function. right? That tells you how far your data is off. And then you could extract out the noise, I mean, the thing is, if you know what the answer is, then you just correct the Y values, I think is the problem. I'm not sure that, but your a priori knowledge. So for example, let's say we're trying to classify between, so we're pretending, okay. So what we're doing is, let me pop this back up. Am I sharing still? I don't think I'm sharing anymore. Yeah, I apologize if I got a little bit confusing in this. What we have is this type of situation. Uh-oh. Now my system's going kaboom. I went black. I know that, guys. Give me just a second. Okay, let's see if we can. All right, yeah, that'll do. So what we have is this situation. We know what the line is, but we know what the line is because we're assuming there was a line out there and we're generating some synthetic data. Right, so we start off with this line. And this line is y equals 0.1 x plus 0.3. So that's the actual answer. We don't actually get to use that when we're running our algorithm because that's data that we're not actually supposed to know, right? But we use this to generate some random x values, right? So we pick some random x values, and then for each x value we generate a y that's just a little bit off of that line by throwing in some noise. So that's the cloud we see. Now at this point we forget we ever knew this. Okay, so now we just completely erase this line from our memory. And now what we want to do, so the idea is there was some ghost out there and they generated some data and they did it to communicate with us from the far beyond. And now our job is to figure out what they were trying to communicate to us by generating a line that actually matches to this. So what we do is we start out by assuming that m equals 0 and b equals 0. Right? So this forms a line. This is y equals 0. Right? So that forms a line right there. Right? So our red line is our first guess. Okay? And then what we do is we take each one of these points and we calculate the distance of that point to the line. Right? And that becomes our loss function. So our loss is the sum of the squared error of each point to that line. Okay, and now we find out that, well, in order to approach that line, right, we know that we want to move this error down. And as we perturb this line, we find out that by moving M up and B up, that's the direction that minimizes the error, or that's the direction that we have to move in order to reduce this loss function. So now we move in that direction and we pick a new M and a new B, maybe like this. And then we calculate a new loss based on the distance to this line, right? And we calculate again, and now we find out that we still have to move both of them up, right? And now this time, maybe we move to there, and maybe we have B is pretty close, maybe, but both, we calculate the distance of each point to the blue line, update our loss, and now we find we have to move at least the slope down, and we keep doing this over and over again, each time making our error actually go down. Okay, so we don't actually know. The assumption is when we're actually running this part of the loop, we don't actually know what the real value is. Okay, otherwise it would be really simple, right? We just would pull out the M and the B. But that's the basis behind what we're doing. We're marching down a curve in order to get... so the error is the distance between the dots and the guess line. So we're going to guess a line, we're going to calculate the distance, and then we're going to use the gradients to figure out what direction we have to move our guess in to get closer. Right, and that's exactly, by the way, what you're doing with these neural nets. Except this time, the answer isn't how far from the line it is, but let's say we're trying to classify cats and dogs. It's how many cats you got right versus how many dogs you got right, or how close your percent certainty of it being a cat was. Okay? Yeah, I've had that before, Kevin, by the way. I think we're actually done, so I'm going to let you guys all go. Enjoy this lab. This is a fun lab. And we'll talk a little bit about data curation at the start of the lab, because that's actually the hard part of the lab. All right, we'll see you guys later. Oops.